All right, good morning, everyone. This is good on the sound? Yeah, great. Good, okay, so, well, as you can see, I'm actually, I didn't update the title of my talk, I should have. What I'm actually planning to do is tell you about stellar remnant populations in LISA as they are noise, tools, and sources, so different things. The binaries that come from stars are, they have a lot of ways that they integrate with LISA. So we're gonna go through all of them. Before I start, I wanna thank the organizers for allowing me to give this talk. It feels a little bit full circle because my very first conference was a LISA symposium. And now I'm here with a student who has this as their big first conference. And the fire alarm went off during her talk. So I'm starting off on a really good foot. Hopefully the fire alarm doesn't go off during my talk as well, but we'll see if lightning can strike twice. Okay, good. Let's get started. So many of you may know this already, but just to be sure, short period stellar remnant binaries are really great millihertz gravitational wave sources, and that's just because they have short orbital periods. Many of them are close by, many of them are in the galaxy, and many of them don't have tiny, tiny chirp masses. So when you put a standard binary in, you get pretty strong strains. That's maybe not so surprising. However, stellar remnant binaries are the product of many, many, many physical processes that shape both the size and properties of any given population. And so what I want everyone to understand, though, from this talk is that stellar and binary evolution is not a black box. I think many people, when you hear the words galactic binaries, you think this is the foreground. Then us star people come in and say, we actually don't know the height of the foreground, and then everyone gets scared because maybe the height of the foreground is 10 times bigger than you have heard before, or 10 times lower than you have heard before, and that's scary when the foreground is the largest noise source and part of your frequency band. So what I hope to do with this talk is convince you that all of these foregrounds that we're producing are the result of actually physical processes, and because they're the result of physical processes, as we continue to understand the physics of these systems, we'll give you better foreground predictions, but they will change over time. All right, good. So I'm a person who loves stars, and I couldn't miss an opportunity to teach everyone here who may not be an astronomer some stellar astrophysics. We're going to go fairly quickly through this, but I do want to make sure that everyone really genuinely does believe us that when we are making population synthesis predictions, these are grounded in real physics. It's not just a giant black box. So say you start out with 2 stars. I have timescales here. The top timescales are for things like black hole and neutron star progenitors. The bottom row is for things like white dwarf progenitors. You can see the timescales here are kind of dumb because white dwarf progenitors can live for a very, very long time. So that's why those don't really make any sense. Good, okay, so you start out with a binary. The most massive star is going to first exhaust the hydrogen in its core. When it does so, its radius is going to expand significantly as it climbs the giant branch. And when it does that, because it has a companion, it can fill its Roche lobe. One thing that it can do when it fills its Roche lobe is just continue to stably transfer mass here. And as this mass transfer happens, what happens to both the stars and the binary depend on the physical properties of the envelope of this star, but also how the orbit itself responds to the mass transfer. If mass transfer is transferring from a heavier object to a lighter object, the orbit will shrink, and vice versa. If it actually goes through a mass ratio reversal, then the orbit will begin to widen. We understand this because it's literally just angular momentum. Good. Eventually, the envelope will be stripped, leaving behind a stripped star. If this stable mass transfer is conservative, you can potentially donate a bit of mass, or in the case of black hole progenitors, tens of solar masses of material. That object will usually pretty quickly, after its strip state, reach the end of fusion in the core and produce something like a white dwarf neutron star or black hole. I made it gray here, but whatever. If it is a neutron star or a black hole, there could be a natal kick that could unbind this binary. Okay, good. Then this star now is going to exhaust hydrogen in its core, could advance off the giant branch, begin accreting. This is something that we see quite a lot out in our galaxy and other galaxies. X-ray binaries, cataclysmic variables. This is a fairly long-lived stage. You get a strip star, stellar remnant formation, and then here, gravitational waves take over to bring you to a merger. In the case of white dwarfs, in between here, things like tides can start to work because white dwarfs have radii. When you get real close, maybe tides work in neutron stars as well, too. So this is one path, and this is often what we would call a stable mass transfer path, because only stable mass transfer happens in the system. You could, of course, go into something else, which we call a common envelope. This is a very uncertain phase, but the two stars are orbiting in the same stellar envelope, and what we know about this phase is that it is likely that the orbit will shrink very significantly because there's none of this going in and then going back out phase. It also happens much more quickly. We think it happens on a dynamical timescale, and usually, as I said, produces closer binaries. But then the same idea, double stellar remnant formation, gravitational waves take over to shrink and circularize you. Good? Easy? Everyone just took their first 5-minute version of my STARS class. Great, congrats. Okay, this is one phase. Now, of course, you might not be surprised to know that you could start out doing the common envelope phase. We're not going to go through that because we don't have time. But these are basically all of the processes that underpin the formation of our LISA sources that are these last two phases. There's a lot going on here that we don't fully have described yet, and this is why the foreground predictions change all the time. I see this as an opportunity to learn about a lot of physics that's going on here, and LISA will give us this last endpoint to all of these sources. The other thing that I want to show is that many of these phases have already been directly observed, and many of the people who have worked on this are sitting in the room here, so you have an opportunity to go talk to them and ask them about these populations. But what I really want to impress upon you is that LISA here is, when it flies, it's going to be joining a massive host of astronomical observatories, and we cannot forget that those astronomical observatories are telling us information too. So we really do the best when we combine everything together. Good, okay. The other thing is these processes that I just worked you through basically underpin everything that we understand about stellar remnants. And in particular, there is this synthetic catalogs synthetic UCB catalogs project that I'm leading with Alexei Bobrick. And we are working in the Astro Working Group to try to understand how these uncertain physical processes are implemented in our codes and how they make their way through to the foreground. So everyone's working on this. Stay tuned. We'll see what we get in some months. All right, so now that we have that figured out, I'm going to tell you about, once we have a bunch of stellar remnant binaries, how do they actually make a noise source in LISA? So we have a bunch of double white dwarfs here. The vast majority of the LISA sources will be double white dwarfs, but maybe there's some neutron stars or maybe there's some black holes. And I like to think of LISA as a big old set of buckets, and you put the systems into their respective frequency buckets. If you do that for the whole galaxy, what you find is that because all of these sources are driven by gravitational wave evolution, and this frequency power is so dang strong, you end up with many, many binaries down here and many fewer binaries down here, because binaries at 0.05 millihertz evolve 2 million times slower than binaries at 5 millihertz. So they start out slow and they zip through. This is compounded by LISA's frequency resolution. So say LISA's observation time is 4 years. That gives you a frequency resolution of 10 to the 8 hertz. That means that down here, where you've put all your binaries because of physics, there's actually fewer bins to resolve them in the first place. So many binaries, so few bins. What happens? An astrophysical foreground. When we actually do this, this is from a paper that I wrote with Sarah Thiel, who's now a grad student at Princeton. You can add up all of the double white dwarfs in the entire galaxy, and you see this characteristic shape that gives you this little bump in the LISA frequency sensitivity. There's also a nice feature here where they stop right at about 10 millihertz, and that's because double white dwarfs start to interact in the LISA band. The white dwarfs have a significant radius, so they can start to interact. Many people in our community have studied these things, including myself. We don't often include them in the foreground because once they start to transfer mass, they either zip this way or zip that way. And if they zip that way, their mass ratios get significantly lopsided so that they don't appreciably contribute to the foreground. Here is where we often think of the binaries as being resolved or unresolved. So right at about 1 millihertz, there's just so many systems radiating with the exact same orbital period, according to Lisa, that we'll never tell them apart. And this is where we get the canonical statement that there are tens of millions of binaries in the foreground and 10,000 binaries that might be resolved. Cool? All right. This is not just me. Sarah was not the first person to do this. We've been doing this literally since the 60s. Lipanov and Postnov knew that the double white dwarfs would probably form a foreground for gravitational wave sources all the way back in 1967. Pete Bender and Ron Webbink made a paper that I read 1 million times in the first 3 years of my PhD to try to figure this stuff out. And many people over the years have been doing this. And every time we put a new paper out, it's a refinement because we have new physics that we're trying to understand and include. What we do know for sure is that there will, no question, 100%, there will be millions of binaries radiating in the Lisa band, and we will be able to find them. And one thing that I want to highlight here is that they will be excellent astrophysical tools, specifically just for studying the Milky Way galaxy and its neighbors. Aside from all the binary evolution that I just showed you, we can actually use them as nice little test masses all throughout the galaxy. The reason for that is because Lisa can see these things very far away. So up until 2019, this was our complete sample of white dwarf binaries. White dwarfs are really dim. This is literally us, right in the center here. And when we put Lisa on here, double white dwarfs are extremely loud signals. So if you're at a 3 millihertz frequency, you are resolved to inside the galaxy fully. That means that we have a complete sample. Coming from the astronomy side, this is literally a mind blower because we don't get complete samples ever. And the fact that we can just know for sure that we caught them all is like an absolute game changer. This is genuinely unspeakably large, the impact here. We don't get this. This was our complete sample. Okay. If we get these things, the double white dwarfs will literally show us the shape of the galaxy. This curve that you see here is the shape of the galaxy in angular coordinates. This is from a paper that Astrid Lamberts led. And what you can see immediately is that the shape of the oldest populations are extended off the disk. This is something that we expect from electromagnetic surveys, and Lisa will confirm that the same thing is true, that the youngest populations mostly are in the disk, the oldest populations are off the disk. Dope, very cool, love that. Lisa can also measure the individual shape of different galactic components. This is something that Anne Marcia is working on with me, and we're including updated models for the triaxial shape of the halo. We'll see the triaxial shape of the halo through these resolved sources. And we can also, as Valeria Coral showed, see these sources all the way out, potentially to Andromeda, but definitely the local Magellanic Clouds, satellite galaxies, things like that. Not just double white dwarfs, Lisa will also see some other things. And oh wait, I skipped ahead, sorry. We'll also be able to see double white dwarfs with telescopes. Once we know where their frequency is and where they roughly are in the sky, we can point telescopes to find them, and eventually we'll be able to map all of the white dwarf merger landscape that produces a whole host of transients, things like type 1a supernovae, dot 1as, R-core Bohr stars. Lisa will tell us where all of these things are, so why not look at them? Good. And then finally, Lisa will be able to give us orbital evolution measurements, these F dots. And if we get an EM distance measurement, we can map out the F dot to GR and get precision accretion measurements on how things like mass transfer and tides are changing the orbit of double white dwarfs. So Lisa's sources for double white dwarfs, both resolved and unresolved, is going to be a huge game changer for understanding astrophysics. And now I say not just double white dwarfs. The thing that I want to point out here is that every ground-based gravitational wave source either forms or passes through the LISA band. And as it does so, if this starts out in LISA as an eccentric source, by the time it makes it to LIGO or Virgo, there's not any eccentricity to see. And so that's sad for them, but will be amazing for us in LISA. How many of these things are we going to see? When LIGO first found 150914, very shortly after, Alberto Cezanna wrote probably my favorite paper in all of history so far, which was to show that if you wind it back to LISA, LISA would have seen GW 150914. And what I want to impress upon you is that LISA could have told us what the formation environment was for 150914 had it been flying. So we think these rates, I could talk about these rates for way too long, and I'm going to say nothing, because I'm going to lose all my time, but I'll talk to you about these rates if you want to later. We also simulate forward models to predict rates as well, and we're not super, super, super off. Same-ish orders of magnitude. I don't really care about the rates so much, because if we can find them, every single binary that LISA observes is likely to have a measured chirp mass, because these things are chirping. They're massive enough that they'll be chirping in LISA, will have an eccentricity, and they just literally have a dynamical origin tag on them if you measure their eccentricity. And not only that, as what Kyle Kramer has showed, is that they have like levels of dynamical activity in each source. So in green, I'm showing you systems formed from isolated binaries. In blue, these are binaries formed in globular clusters, but then ejected, and they merge quietly outside of the cluster. And here, these are systems that form in the cluster and merge in the cluster at an extremely dynamically active place, where in LISA, if we see these kinds of eccentricities, we literally know that that binary black hole is in a globular cluster. That's pretty cool. Does anybody know where any of the LIGO black holes have formed ever? Totally, we don't. LISA, when it launches, may do more for formation channels that LIGO is observing than LIGO will do. Good. Neutron stars won't be left out either. There's currently uncertainty about how many neutron stars there are in our galaxy. If we just look with radio telescopes, we see about a factor of 2 to 10 fewer double neutron stars in our galaxy than the LIGO rate. And what I showed with Jeff Andrews is that if the binary neutron stars have a high eccentricity and a fast merging channel, LISA can see them very obviously. If there's a fast merging channel in the dynamical formation, you see them all the way up here. If there's a fast merging channel in the isolated binaries, you see them way down here. Easy peasy. So LISA will also tell us about the formation environments of neutron stars. All right. Oh, okay. Okay. 2035 is coming fast. When I started grad school, I started in 2013. I've lived for the past 10 years with people saying, oh my God, LISA's so far in the future. And my answer has always been it's better than infinity, because it was infinity when I started. And now we're all really scared. 2035 is really fast. We have to build the whole thing. That's crazy. But also, in astronomy, 10 years is a really long time. And it's almost outsized how long it is for stellar populations, because we are literally in a golden era of photometric, spectroscopic, and astrometric surveys. And these things are providing extremely precise characteristics of enormous binary populations across the Milky Way. I don't have time to go into it, but I have a little teaser, whatever. You can ask me about it more. But basically, every single thing that we understand about binary stars is going to either change or be standardized by the time LISA flies to an extent. There will still be uncertainties, but the time between 1967, where Lyapunov and Postnov were predicting things, to now, we're probably going to make the same advances from then between now and when LISA flies, because the amount of data that we have on binary stars is going to be astronomically large. One example that I want to highlight here for how this actually will change things for us is this nice population of cataclysmic variables. One of the first things that I learned about cataclysmic variables is that they are white dwarfs accreting from hydrogen-rich stars, like main sequence stars. That happens in a wide-ish binary, and these things are so bright and so common that we can pretty well describe their physical characteristics. You can see the data here. The binary starts out. It starts filling its row slope at about 6 years. It continues to shrink here while the secondary mass goes down. The mass is like donating, that's why it goes down. It shrinks here because of GR and magnetic braking. Then the star goes fully convective, and so it's not actually transferring mass anymore, and GR takes over. That's why the mass stays flat. Then it starts to transfer mass again, and eventually the star changes the phase again and has this turnaround period. This turnaround period, you can see, is longer than an hour. And so stories, have been, look, LISA is great. It's probably not really going to see anything with the CVs, because when you look at the orbital period bump that happens at this turnaround where everything piles up, it's just too long of an orbital period. Paula Scoti, who is like the CV queen, told me this a long time ago and has continued to tell us this even after we wrote this paper with Simo, oh my God, I left an eye off, Simo Skaringi and Tyson Littenberg. And so what we did here was we said, okay, look, the story is CVs, they'll never show up in LISA, but Gaia gave us distances to a bunch of CVs in 2019 in DR1, and Anna Paula calculated the complete sample of CVs in the local neighborhood of the sun, and it turns out there are a lot of them, like really a lot of them. Even within 200 parsecs, there's several dozen CVs here. And so what we did in this paper is we just took Anna's data and we scaled it out to a kiloparsec instead of 200 parsecs, it's all empirical, this is no models. And we said, oh my God, look at this. This is the LISA curve. And some of them do poke above the sensitivity curve. So maybe they'll be resolved. No, they won't be resolved. And the reason for that is because we won't be able to measure their chirps. So it's going to be very difficult with just a strain to know that each of these things is a CV. However, because we had Tyson on our team, we can also look at literally what the confusion is when you add the CVs. You can see it just in the data that there's something going on here. Once you try to subtract them out, if you just include white dwarfs, you get kind of what you would expect from the confusion. But the CVs produce a significant foreground bump. And this foreground bump tells us exactly how many of them there are in our local neighborhood, because we know their evolutionary states. So there's two things that you need to be thinking about here. If you're a person who wants to get rid of all this stuff because it's trash and you don't really care, you need to get ready to subtract out some weird shaped trash, because stars have shapes in them, and this is just one population. If you're a star person, this is a massive opportunity. There's tons of stellar populations in the galaxy, and this tells us a ton about these types of systems. The coolest part is that this period minimum, we actually don't know what it is very well, because these systems get really dim. So LISA, where we get this little drop-off, is going to tell us exactly what the period minimum is for the CVs. That's cool. All right, this is one example for one population. Over the next 10 years, we're going to get ridiculous constraints on things. Don't be surprised when I come back and tell you that the foreground is a little bit different, or that the number of sources is going up and down by factors of few. It's impossible to predict what we're going to learn. Gaia DR4 is coming out not before the end of 2025, but definitely before LISA flies. Gaia DR4 is going to tell us literally about millions and millions of binaries in our galaxy. So everything that we know is going to be updated. With that, I'm going to leave you with some takeaways. I just want you to remember, binary interactions shape the rates and features of each population. These are physical things that we do understand how they work. It's not a black box. LISA will play a critical role, but not a singular role in the understanding of stellar remnant binaries. LISA is joining a fleet of astronomical observatories, and we need to make sure that we maintain those ties to the astronomical community. And finally, electromagnetic surveys are going to provide critical constraints for the progenitors of LISA sources. Population modeling refinements are likely to modify this story that we've been telling you since the 60s. And I'll take questions.
Thank you. Questions for Dr. Breivik?
Hey, Katie, this was a great talk. So there will be a fleet of other observatories. Is there something you think is missing? Something we should really be careful about in terms of preparation or EM follow-up to be ready?
Yeah, so let's see. Extras. This. OK. Binary stars go through all of these phases. These are all of the things that we need. One thing that I never show on here is support for UV. I think UV support is something that the astronomical community needs to really reckon with. Hubble is as old as I am. And when it goes out, we're dead. Like, there's not really something to replace Hubble with. And Swift is definitely not going to do it, because Swift is also literally falling out of the sky. So support UV telescopes where you can, because I think that that's something that we aren't going to get very well with photometric, astrometric, and RV surveys from the ground.
I felt tempted to ask about Gaia DR4.
Yeah.
And also, generally, which community should Lisa be talking to the most in terms of observations?
I think it depends on the sources that you care about, but I think that the role that Gaia will play in understanding the LISA progenitor sources, and actually also the LISA sources that we know now, the verification binaries, like, really can't be overstated. I think Thomas Kupfer has shown this very handily, that when you update models or update our known information on the verification binaries with the addition of Gaia data, we get way better constraints. So that's extremely biased, though, because I also care about Gaia a lot. But yeah, like, that's, I don't know. I think pound for pound, Gaia is one of the most important surveys of all time, because it just tells us literally where everything is, how fast it's moving, and how big the binaries are. So, yeah.
Hi, thank you. On the topic of sources moving from LISA to ground-based bands, do you have an estimate of what sort of timescales those would be on? Is it going to be we see a source in LISA and then 100 years later it shows up in LIGO or successors?
Yeah, no. So we actually do have it. Alberto wrote it in the paper, which is fantastic. It's like 5-ish years for like a 150914. So LISA can tell ground-based detectors, please don't turn off during this time because something's coming. And then we get ridiculous tests of, like, GR, for example, because something that chirps from 10 to the -3 hertz all the way into ground-based detectors, that's a really cool, like, time measurement for GR to continue to work. But yeah, 5-ish to 10-ish years, depending on your mass.
Great, thank you.
Yeah.
Are there any other questions? Other questions? Okay. If not, let's thank the speaker again for the talk.